Let's take a look at something many find quite difficult to understand. We're going to have a look at half-life. So, what is half-life? Half-life of an atom is the average time taken for half of the unstable nuclei in a sample to decay. Well, what does that mean? Let's take the following example. Let's pretend that we have 16 unstable radioactive nuclei from some element. Now, after one half-life, however long that is, we will be left with 8 unstable nuclei. What happened to the other 8? The other 8 turned into something more stable. I know the color scheme here might be confusing, but the blue ones are unstable and the red ones are stable. What do I mean by stable? I mean they won't give out any more alpha, beta, and gamma. Now, in reality, that's not what happens, but for the purposes of IG and in the interest of simplicity, it will do you well to think like this. So, 16 radioactive atoms. After one half-life, we have 8 radioactive atoms. After another half-life, we only have 4 radioactive atoms. And after another half-life, we only have 2 radioactive atoms. What are the rest of them changing into? They are changing into something more stable. Now, why do we call it half-life? Well, basically, from 16, we divide by 2, we get 8. From 8, we divide by 2, we get 4. And if we divide by 2, again from 4, we get 2. If you do it again, you're going to get 1. Now, the key is, how long does this take? How long does this halving process take? This is what is known as half-life. Basically, the time taken for the activity to halve. Now, when I say activity, I basically mean on the Geiger-Müller tube, when we see those counts, how long does that take to halve its previous value? So, to understand this better, let us have a look at a couple of questions. A radioactive substance has an initial activity of 1600 counts per second. 12 hours later, the activity has gone down to 200 counts per second. What is the half-life? Well, you've got to figure out how many times we have to halve 1600 in order to get it down to 200. So if you halve 1600 once, we get 800. You halve 800, we get 400. We've halved it twice. You halve 400, you get 200. We have halved it 3 times. So what's the half-life? Well, it took 12 hours to do this. And we've halved it 3 times. That basically means that each half-life was 4 hours. Why? 1600 halved once, 800. 800 halved again, 400. 400 halved again, 200. That'll be 4 hours, 8 hours, and 12 hours. The half-life is 4 hours, 12 hours divided by 3. What that basically means is, to go down to 100 will be another 4 hours. To go from 100 to 50 will be another 4 hours. Now, there's one curveball I would like you to pay attention to. Sometimes you might be asked, well, what was the activity 4 hours before the beginning? Now, the beginning here is the beginning as we see it, not the beginning of the radioactive decay. As far as we were concerned, it was 1600 at the beginning. However, what was the activity 4 hours before then? Well, instead of halving it, I hope you can see you're going to double it. So the activity before 1600, 4 hours earlier, was 3200. Just like to go from 400 to 800, you would have to go backwards 4 hours and double it. I hope that makes sense. Here's another question. A radioactive substance has a half-life of 2 hours. If the initial activity was 120 counts per second, what will the activity be after 6 hours? Well, This time they're doing it in reverse. They're giving you the time. Now we know the half-life is 2 hours, yet the total time is 6 hours. How many times does 2 hours fit into 6? It fits 3 times. So how many half-lives do we have? Well, we have 3 half-lives. And what you're supposed to do is take the 120. Not only do you halve it once, which is 2 hours, to get 60. Not only do you halve it twice, to get 30 after 4 hours, you have to halve it 3 times each time, which will give us 15. So I hope you understand, 2 hours later, it'll be almost 7.5. You wouldn't call it 7.5, you would round it, but let's just say for argument, it was 7.5. I hope you understand if I asked you, let's use this as our starting point and figure out what the activity is 4 hours before. Well, we know the half-life is 2 hours. So basically 4 hours before is 2 half-lives. So I don't halve it once, I don't even halve it twice. I double it twice because I'm going the other way. So double 120 would be 240, double 240 would be 480. So the activity 4 hours before here at 120 would have been 480. How do I know? Because I know the half-life is 2 hours. So 4 hours backwards is 2 half-lives. Let's take a look at a typical decay curve. So here we've got an activity of some radioactive source of 400 counts per second or counts per minute. Looks like counts per second here. And when I play this, you're also going to see this diagram where a radioactive nuclei becomes a stable one whilst giving out either alpha, beta, or gamma. The thing I want you to understand, however, is we cannot predict which nuclei will decay because radioactive decay is completely random. I can't tell you which one will decay next. Now, the purpose of the slide ultimately is to help you find the half-life using a graph. Well, if the initial activity is 400, then half of 400 is 200. And what I'm looking to do is find out how long that took. That took 10 seconds. That means every single 10 seconds, its activity will go down by half. What's half of 200? It is 100. Notice it took 20 seconds, but it only took 10 additional seconds. So how long would it take to go to 50? It would be 30 seconds in total. It would be another 10 seconds. If I asked you the activity 10 seconds before 0, in other words, if we went back the way, well, if we know the half-life is 10 seconds, we don't halve it this time, we must double it, so the activity would have been 800. Here's another graph. I hope when you look at this, you can tell me that the half-life of this radioactive isotope is 2 minutes. How did we find that out? Well, the initial count rate is 1,000. Half of 1,000 is 500. How long did that take? 2 minutes. I hope you then understand for it to go from 250 down from 500, it would be 4 minutes in total. It would just be another 2 minutes. To go down to 125 from 250 would be another 2 minutes. Half-life is basically the time it takes the activity to half its current value. And in general, that time is always the same. There's the second half-life, the third half-life, as I mentioned before. Background radiation. What is background radiation? Well, we discussed it previously, but basically it's already there. It's already in your room. It's round about us everywhere, and there's not a lot we can do about it. We've got 2 rows in the periodic table that are essentially, more often than not, radioactive. They exist on Earth, so we have background radiation as a result. there is naturally present radon gas in the atmosphere. We have background radiation as a result. And there are cosmic rays coming from the sun. Again, there's not much we can do about that, so background radiation exists. It's small, but it's consistent. In general, anywhere between about 18 to 22 counts.